In this video, we will familiarize ourselves with the properties of cycloalkanes, discussing how the rigidity of the ring structure influences the isomerism and stability of these compounds. Additionally, we will cover the concept of ring strain and its impact on the relative energies and conformations of cycloalkanes. Let's begin with a quick review of everything we know about cycloalkanes. Cycloalkanes are hydrocarbons that form ring structures and have 1 degree of unsaturation. This means that instead of being ordered in a linear chain, the carbon atoms are connected in a loop, creating a cyclic molecule. Cycloalkanes can be thought of as alkanes that have been closed into a ring by removing 2 hydrogen atoms, which contributes to the 1 degree of unsaturation. The general formula for cycloalkanes is CnH2n, which reflects this single ring structure. Some of the cycloalkanes we've seen already are cyclopropane, C3H6, cyclobutane, C4H8, and cyclopentane, C5H10. Now, just as with straight-chain alkanes, substituted cycloalkanes can also exhibit isomerism. Let's begin our discussion of isomers of substituted cycloalkanes using the following example: dichlorocyclopropane. Dichlorocyclopropane has the molecular formula C3H4Cl2, where 2 hydrogen atoms on cyclopropane are substituted with chlorine atoms. Based on the molecule's name, we can draw 2 structures that satisfy this formula. Let's label these structures A and B. The proper IUPAC names for these structures are 1,1-dichlorocyclopropane and 1,2-dichlorocyclopropane. These 2 molecules are constitutional isomers because they have the same molecular formula but different atom-to-atom connectivity. In this example, the molecules are depicted without considering stereochemistry. Let's explore what changes when we redraw the molecules with stereochemistry included. Here, I've redrawn the cyclopropane backbones as they would appear from the perspective of someone observing the molecule from the front. Molecule A can only be drawn one way with stereochemistry, resulting in this structure. For molecule B, however, the IUPAC name 1,2-dichlorocyclopropane leaves some ambiguity regarding the stereochemistry of the chlorine substituents. When observing the ring head-on, the chlorine substituents on carbons 1 and 2 can point either in the same direction or in opposite directions. In other words, the chlorine substituents can be cis or trans. Here I've drawn cis and trans 1,2-dichlorocyclopropane labeled B and C. Because small rings such as cyclopropane are rigid and bond rotation is not possible, we can think of them as analogous to alkenes, where rotation around the carbon-carbon double bond is also restricted. Here we have an example of 1,2-dichlorocyclopropane side by side with an example of stereoisomers from a previous video. In both cases, the rigidity of the structure leads to fixed positions for the substituents, resulting in distinct stereoisomers. In a previous video, we examined A and B, which are stereoisomers with the same atom-to-atom connectivity. A is cis-1,2-dichloroethylene, where the 2 chlorines are cis, or on the same side of the double bond, and B is trans-1,2-dichloroethylene, where the 2 chlorines are trans, or on opposite sides of the double bond. Additionally, C was identified as a constitutional isomer of A and B, having the same molecular formula but different connectivity. Similarly, in our current example of 1,2-dichlorocyclopropane, the chlorine substituents can either be on the same side of the ring, forming a cis isomer, or on opposite sides, forming a trans isomer. This results in 2 distinct stereoisomers due to the rigidity of the cyclopropane ring, just as we saw with the double bond in dichloroethylene. Cis and trans stereoisomers of cycloalkanes are referred to as geometric isomers. Finally, here is one more alternative perspective where we observe the ring structure from above to convey the same point. Now that we've examined the geometric isomerism in cyclopropane, let's delve into the unique reactivity of cyclopropane itself. Among the 4 cycloalkanes, cyclopropane uniquely reacts with sulfuric acid to produce propyl hydrogen sulfate and isopropyl hydrogen sulfate. Additionally, when reacted with hydrogen H2, in the presence of a platinum catalyst, cyclopropane most rapidly undergoes hydrogenation to form propane. Cyclopropane's unique reactivity is a result of significant ring strain. Ring strain occurs because the bond angles of the carbons in cyclopropane are forced to be much smaller than the ideal tetrahedral bond angle of 109.5 degrees. In cyclopropane, the bond angles are approximately 60 degrees, which creates considerable angular strain. This strain makes the bonds in cyclopropane more reactive and prone to breaking. As a result, cyclopropane readily undergoes reactions that relieve this strain, such as its rapid hydrogenation to propane and its reaction with sulfuric acid to form propyl hydrogen sulfate and isopropyl hydrogen sulfate. The high ring strain makes cyclopropane much more reactive compared to larger, less strained cycloalkanes like cyclobutane and cyclopentane. We can calculate the bond angles in cycloalkanes the same way we would calculate the interior angles of a polygon using the formula n-2 times 180 divided by n, where n is equal to the number of sides or carbon atoms in the ring. Let's use this formula to quickly find the interior angles of our remaining two ring structures. Generally, the closer the internal angle is to the ideal bond angle of 109.5 degrees, the less angle strain the ring has. The cycloalkane's ring strain is the result of the combined effects of torsional strain and angle strain. From the last video, we learned that a molecule's torsional strain is generated through simple bond rotation. For example, in ethane, the eclipsed conformation has a torsional strain of approximately 3.0 kcals per mole, which can be relieved through bond rotation to achieve the staggered conformation. In cyclopropane, the hydrogen atoms are also eclipsed. However, unlike in ethane, this strain cannot be relieved through bond rotation due to the rigidity of the ring structure. As a result, cyclopropane experiences both angle strain and torsional strain, contributing to its high energy and consequently its high reactivity. In contrast, the remaining two cycloalkanes, cyclobutane and cyclopentane, are not completely rigid like cyclopropane. They can adopt different conformations to alleviate some of the ring strain. Cyclobutane can adopt a puckered conformation, where three carbon atoms occupy one plane and the fourth carbon sticks out slightly from the plane. Interconversion between the puckered and flat conformations is possible, similar to the behavior of alkanes. However, the ring spends most of its time in the puckered conformation, which is more energetically stable. Finally, cyclopentane can adopt a handful of different conformations: flat, envelope, and half chair. Because cyclopentane has interior angles of 108 degrees, which are close to the ideal bond angle of 109.5 degrees, the ring experiences negligible angle strain. However, the flat conformation, where all adjacent hydrogens are eclipsed, has significant torsional strain of approximately 10 kcals per mole. This torsional strain can be slightly relieved when the ring assumes the envelope or half-chair conformation, but not fully, because the carbon-carbon bonds cannot be completely staggered without breaking the ring. As always, let's do some practice. Identify whether the following molecules are constitutional isomers, stereoisomers, or neither. Feel free to pause the video and try these problems on your own first. The first pair of molecules are two cycloalkanes, cycloheptane and 1,1-dimethyl cyclopentane. These molecules have the same molecular formula, C7H14, making them isomers. Cycloheptane is a 7-membered ring, whereas 1,1-dimethyl cyclopentane is a substituted 5-membered ring. Therefore, these two molecules are constitutional isomers as they have different atom-to-atom connectivity. The second pair of molecules are isomers with the molecular formula C5H9BRO, shown in two different perspectives. The molecule on the left has both substituents cis to each other on the ring, whereas the molecule on the right has both substituents trans to each other on the ring. Therefore, these molecules are stereoisomers as they have the same atom-to-atom connectivity, but differ in the spatial arrangement of their substituents. Let's move on to the next question. Despite well-known disadvantages, the combustion of hydrocarbons remains an important source of energy. In the combustion reaction, the carbon and hydrogen atoms of the hydrocarbons react with O2 to produce CO2 and H2O, respectively, which are the most stable possible products. Suppose you had equal cost supplies of the two isomeric hydrocarbons, A and B, that could be used in an industrial combustion process to generate heat. For a given mass of hydrocarbon, identify the hydrocarbon that would generate the most heat. Explain your answer. Feel free to pause the video and try this problem on your own first. We can determine which hydrocarbon will generate more heat upon combustion by comparing the relative energies of the two molecules. Molecule A and molecule B are isomers of the same substituted cycloalkane, cyclobutane. Specifically, molecule A is cis-1-ethyl-3-methylcyclobutane and molecule B is trans-1-ethyl-3-methylcyclobutane, making them stereoisomers. A cycloalkane's energy is directly related to the amount of ring strain the molecule has, which is the sum of the molecule's angular and torsional strain. Because these molecules have the same angular strain, their energies can be differentiated through their different torsional strains. The torsional strain in a molecule arises from the eclipsing interactions between adjacent atoms or groups. In cis-1-ethyl-3-methylcyclobutane, the ethyl and methyl groups are on the same side of the ring, leading to greater steric hindrance and increased torsional strain due to their proximity. This makes the cis isomer less stable and higher in energy. In contrast, in trans-1-ethyl-3-methylcyclobutane, the ethyl and methyl groups are on opposite sides of the ring, reducing steric hindrance and torsional strain. This makes the trans isomer more stable and lower in energy compared to the cis isomer. Since the cis isomer, molecule A, is higher in energy due to increased torsional strain, it will release more heat upon combustion compared to the trans isomer, molecule B. Therefore, cis-1-ethyl-3-methylcyclobutane, molecule A, will generate more heat upon combustion than trans-1-ethyl-3-methylcyclobutane, molecule B. This difference in heat generation is due to the higher torsional strain in the cis isomer, making it less stable and thus releasing more energy when it combusts. Finally, let's move on to the last question. 4-hydroxyproline in collagen is derived from a proline residue that undergoes hydroxylation at the C4 position through a post-translational modification catalyzed by the enzyme prolyl hydroxylase. This hydroxylation induces a change in the ring pucker, shifting from a C-gamma endoproline conformation to a C-gamma exo 4-hydroxyproline conformation. Explain these results using our understanding of the relative energies of these puckered conformations. Feel free to pause the video and try this problem on your own first. Observing the left structure in this reaction, we see that proline adopts a C-gamma endo conformation, where the pyrrolidine ring is puckered such that the gamma carbon C-gamma protrudes above the plane formed by the nitrogen atom and the adjacent carbons. When the gamma carbon is hydroxylated by prolyl hydroxylase, the addition of the hydroxyl group can introduce steric interactions with the adjacent carbonyl group. This interaction can lead to a change in the ring pucker from C-gamma endo to C-gamma exo, which helps to minimize steric hindrance and stabilize the structure. As always, thank you for watching, and I'll see you next time.